We have Dr. Behnam Jafarpour from the University of Southern California to give a talk on his work on integrated data in physics.
Thank you, Andrew. Hello, everyone. Behnam Jafarpour from University of Southern California. And so I want to start by thanking Energy Simulation for bringing us together again in person to have this summit. And for also thanking you for both remote people and people in the session for attending it. So we recently had a new chair proposal for energy simulation, and the title of that is Subsurface Energy Data Science. And today I will be briefly presenting what the idea is and what we want to do in the chair program. And then I'll focus on a specific research topic that is ongoing in my lab right now. So, okay. All right. So basically, what we want to focus on in this effort is to look at combining data science and system science to develop new technologies for a few select energy systems. We've been having active projects on conventional reservoirs, unconventional reservoirs, and geothermal reservoirs and geologic CO2 storage. And basically, right, okay. The specific research areas that we want to contribute to, and this has been, we had actually a chair program in the past 5 years, and my focus in that chair program was dynamic reservoir characterization, and these are the specific research areas that we will continue working on, but this time our emphasis would be on data science. So the first area is the description and characterization of complex geosystems, mainly focusing on taking advantage of machine learning and deep learning methods to reduce dimensionality. And in a lot of problems that we work on, where we want to integrate data, dynamic data into subsurface flow models, one of the challenges we face is dimensionality and adjusting resolution of our models and making it kind of on par with the information content of the dynamic data. So a lot of our effort in here would go into dimensionality reduction. So the second area of research that you see here is integration of dynamic data into subsurface flow models in an effort to reduce uncertainty and to improve prediction quality. The next area of research is field development optimization. How do we improve decisions related to developing and operation of subsurface flow systems with energy and environmental implications? And lastly, which is really what the main focus would be, how we leverage data science, how we leverage machine learning in order to improve prediction and decision support. So we have 4 posters. I have 4 PhD students here from my lab to represent basically each of these areas that you see on the slide, and basically show how we are using data science in order to develop new techniques to do these tasks. Now, before I begin the main topic of today's presentation, I want to acknowledge all the sponsors that we have had in the past 5 years. And this particular project that I'll be talking about is sponsored by Aramco, Saudi Aramco. And we've had this project for the past 3 years. And the idea here is, so we started to kind of look into how we can leverage data science in order to improve prediction in unconventional reservoirs. And there's a specific reason for unconventional reservoirs that we picked this topic for is one of the main areas where data science can be very helpful is when you either don't have a model, a predictive model, or the model is too complex. And in this particular case, we know that our understanding of complex fracture and well interactions in unconventional reservoir is not as good as it needs to be. So we do have certain understanding about the general trend, the general behavior of these systems, but not as detailed as we wish to have. And then the other side of it is we do have, in the past 2 decades, we have had a lot of development in this area where we have collected a lot of data through repeated factory style kind of drilling and production. What it leads to is a lot of trials of the same experiment, of course, with different wells. But the nice thing is that the wells are almost operating independently. There could be some interaction between wells, but for the most part, the main difference here with conventional reservoirs is that you don't have to worry about well interactions that much, which is a big part of how the field behaves in general. So our objective here is, can we develop physics-informed but data-driven prediction models? And there are different ways to go about that, and I will just talk about one particular approach that we have followed. So here's basically our idea is to combine machine learning and domain knowledge in order to kind of combine the strengths of both approaches to develop improved predictions approaches. So if you look at basically the 2 sides, we can have, so what we want to do really is we want to have a mapping from our formation and completion properties to our production data. That's ideally what we want to do. And the way we want to approach it is to combine data-driven tools with simulation technology and see how we can go about this problem. So the data set, the first 6 months of this project was heavily invested in collecting data, or not really collecting data, but gathering data from different sources and kind of cleaning the data, organizing it in a way that you could actually bring it to a data-driven framework and use it. And that involves a lot of work in terms of going to the right website, downloading information, and sometimes those information came in the format of PDF file that then the students had to write a script to kind of extract the information and organize them so that they can become usable. But in general, we have focused on 2 data types, 2 fields basically, the Bakken and the Eagle Ford. Part of our project, we have had several publications on this project, but part of our effort has been focused on what we call transfer learning, which is not what I'm going to talk about today. But the idea of transfer learning is that can we use the knowledge that we gain by analyzing a lot of data from one field in the hope of using that knowledge and transferring to a different field and trying to apply it there. And this is an ongoing work, and we have had we have had a few publications on it. But what I'm going to talk about today is really how to combine physics and data in order to improve prediction. So I'm not going to go into the details of our architectures that we use for our prediction models, but very briefly, what I want to kind of cover here is that, so the idea is having a simple architecture where you can actually reduce the dimensionality of the data. So basically compactly represent the data that we have. What you see on the bottom here is a convolutional autoencoder that tries to reduce the dimensionality of the data that we have, so that the top part, which is a regression model, will take the inputs of the formation properties and completion properties and try to create a mapping between those properties and the lower dimensional representation of the field data. So that's basically the gist of what is done in this architecture. And basically, if you just focus on the data, on the field data, this is an example of training a model, as I showed before, training these kind of models with a lot of data from the field and looking at some test cases, wells that have not been used during your training, to see what kind of prediction you can have. And you can see the data generally tends to be a little bit noisy. And even though you capture the general trend, but our hope was we could actually bring in physics and actually improve these results. So that's what I'm going to focus on. And the question is that, why would you incorporate physics? So the idea is that if you use data only, then field data tend to be complex, incomplete, and noisy. So you have to deal with that complexity of the data itself. Then one of the weaknesses of machine learning techniques in general is extrapolation. And inevitably, you're going to have to deal with that because one of the things that we are struggling with is when we predict in time. And since there is a trend, predicting that trend, if you haven't seen data in that range during training, can be very challenging. The physics can help with that. And then the other aspect to it is the machine learning models. One of the criticisms is that they tend to be black box models. So you don't know how they come up with predictions. You know they're trying to capture trends and correlation structures in your data and use those for predictions. But at the end, the mechanism is really not that clear. And then finally, we do have simulation models that provide causal relationship. That becomes very important when you're trying to do long-term prediction. And that's an advantage of using a simulation model. But if you use only physics, the problem that I mentioned at the beginning, the physics is not very well understood, so it's not that reliable. And then there are a ton of data out there that you can use to improve what you can get out of just a physics-based prediction. So these are kind of our motivation to move toward integration of physics and data-driven approaches. Now, the main question is how. So you want to combine machine learning approaches with physics to bring in some physics. And we are actually doing that in a number of projects. This is not the only project where we are trying to bring physics into our architectures. And we have used different approaches. The one approach that I talk about today for this project is what we call residual learning. So the idea is very simple in residual learning. So instead of loading our data-driven kind of approach to carry the entire prediction task, what we do, we actually try to use simulation model as a baseline prediction, because there are some correlation relationship, functional relationship between important variables we care about within our physics-based models, but they're not detailed and they may not be as accurate as we want them to be. On the other hand, we do have the data from the field, which is shown on the right-hand side. So what we want to do is basically look at what the physics-based approach provides as a prediction, as a baseline for prediction, then look at the residual that is left, which is the difference between what we observe in the field and what this physics-based model provides us. Now, this is where the physics-based approach has not been able to kind of provide as accurate of a prediction as we want to have. So now we bring in our architectures trying to learn what is left to be, to kind of improve our prediction from the physics-based approach. So this general approach is basically what we refer to as residual learning. And the idea is you bring your physics, but you use your data in order to improve the prediction from the physics. And this is another schematic showing basically the architecture that we use in pictures. So on the left-hand side, those are our completion and formation properties. On the right-hand side is basically the residual that you get. And the way we create these residuals, let's say we have 1,000 wells from Bakken in this case. What we do, we generate our simulation models for those, and we actually do predictions. And for each of those cases, we look at the residual between what's observed in the field and what is predicted by our model. And then that will give us, let's say, 1,000 cases, different cases of residual data that can be used for training. And then we use that in order to understand or learn the difference between prediction and observation. Now, when it comes to the physics, we want to keep the method very general. And this is basically something that can be done with analytical model if if there is no simulation model for the particular field that is under study, we can use analytical models. We could use simulation models, numerical simulation models, or we could actually train a network that tries to mimic the behavior of a simulation model. Any of these approaches can be used to represent the physics in this approach. So let me show you a couple of examples, and I conclude my talk. So here's an example. We wanted to test this approach and see how it works. So we actually have had our simulation model on the left-hand side without any natural fractures. So what is missing in this physics-based model is the presence of natural fractures. And the data, on the other hand, is coming from a model that has natural fracture, interconnected natural fracture in it. So we wanted to see if you wanted to use residual learning, can we actually pick up what the natural fractures are actually contributing to the production trend? So we did that, and what you see in here is obviously the physics-based model has an underestimation of the production because natural fractures and the contribution to production from natural fractures would be absent in our physics-based model. And what you see on the bottom are the residual, bottom right here, are the residuals that are calculated and used for training a network. And as you can see, there is a clear structure to this, to the residual. So it was obvious to us that our architecture should be able to pick that up because there's a clear structure there. So this is basically the results showing on the right-hand side. What you see is basically after adding the contribution from the network to the baseline prediction from the physics, we are able to actually follow the trend that is coming from the data. So this was a very simple example to just demonstrate the concept. Now, in reality, there could be a lot of things missing in our models, right? Here's another example showing if the situation was such that there are multiple effects that are missing, and they could actually interact with each other, and the response could be very complex. Are we able to do that by using this approach? So in this case, the example that we're using, we have the physics-based model doesn't have these features, and the natural fractures is one of them, then heterogeneity in reservoir properties, unequal hydraulic fracture half-lengths for different stages, and then fracture closure due to geomechanical. In other words, the data that we have collected has all of these effects in it, but the physics-based model doesn't have any of it. So when we look at the trends now, we'll see that in this case, it's not a clear underestimation or overestimation. In some areas, you have underestimation. In some areas, you have overestimation. So it's a little bit more challenging for the network to pick it up. But because these networks are very powerful in terms of what they can capture, the relationship that they can extract from data, they actually did pretty well in our test here. You can see here, by adding that residual that is learned through our neural network model, we are actually moving from our baseline prediction toward the actual data observed in this complex case. So with that, I want to actually summarize by saying that data-driven models for unconventional wells, our motivation is because of the complexity of the physics and the abundant data from the field, there is an opportunity here for data-driven methods to help with predictions. But if you just focus on data only, then the data-driven methods are statistical in nature, and they're not very good for long-term predictions and when it comes to extrapolation. Now, integrating physics with data, the physics offers imperfect, but still helpful relationship between variables of interest. And the data helps in capturing the missing parts in the physics. That way, we're kind of, the two methods are helping each other. And then residual learning is just one flavor or one approach to combine physics with data-driven approaches that where the physics provides a baseline prediction and data is used to make corrections to that prediction. And with that, I want to acknowledge our sponsor, Aramco in this case, and of course, energy simulation. This has been a 3-year project, And we have had monthly meeting with Aramco, a lot of field-related insight coming from Aramco to help us with the way we approach the problem. And in particular, our collaborators are Ravi Waidia and H.H. Liu and Jilin Zhang, who has been meeting with us and helping us with this project. And the particular topic that I discussed, my students who are here, Shamil and Jodel, are the ones who has done the work, and they are here to answer all the tough questions. All right, with that, I want to thank Aramco again, Energy Simulation, and CMG Limited for providing software that we've used in this project. Thank you very much.
Thank you. Thank you, Dr. Jafarpour. There's a question online here from Isabella Oliveira. Hello, thanks for the talk, Professor. Could you explain better how do you train the residual data? What is the method utilized?
So let me actually go back. So this is a relatively simple architecture that we're using in here. So this architecture, what we have here is basically what we call a convolutional autoencoder on the bottom. What it does, it gets rid of the correlation structure that exists in the data. And by getting rid of that correlation structure, it enables a projection into a low-dimensional latent space. Now, within the low-dimensional latent space, now we need to provide or construct a mapping from our input parameters to that low-dimensional space, which in this case would be a very simple architecture that does regression. Now, this whole architecture is trained simultaneously. I didn't go into the details, but there are basically three pieces in here. There's an encoder that goes from the data into the latent space, low-dimensional latent space. There's a decoder side that takes us from the latent space back to the original data space. And there's a connection to the latent space, from the latent space to the parameters. Now, there are two objective functions that we minimize during the training. One objective function is to make sure that the data is reconstructed, which is the part that is played by autoencoder. And there's another objective function that makes sure during the training we get a good fit from our input variables to our latent variables in the that represents data. So there are two components that are minimized during training. I'm not sure if that's the question.
Okay, question from the floor here.
Laurent from IOGC, thanks so much for the presentation. I'm just wondering, do you think, based of the complexity that usually those unconventional reservoirs they have, with this proposed method, even data science and the physics both combined, would be able one day replace the really reservoir simulation modeling for the industry? Because what we've seen so far, even though reservoir simulation has been improved a lot, but it's really, really hard to rely on that.
Right.
Mainly in a thermal, I'll give you an example for the thermal because it's very complex. We barely can understand how pad to pad, which is roughly 200 to 500 meters apart, how they do. We cannot really understand it. How do you think this method can really replace and help to predict accuracy? Thanks.
Okay, thanks. That's a good question. So the idea here is really not to replace reservoir simulation for unconventional. The idea here is really to improve on it. So if, for instance, the crudest approach you could use is to just take an analytical model to do the prediction, right? And you know you'll be disappointed with those results. But at least there are certain correlations that we believe in general hold, even in that simple model. What we're trying to do here is we are trying to use that to help the data-driven model. So in essence, it's not so much replacing reservoir simulation, it's augmenting it. So if you go from there to, let's say, a few years down the road where you have simulation technology for unconventional, which is a lot better than what we do today, it just makes it easier for the data-driven approach to make improvement, because the baseline prediction is much better than what you have. The other thing I want to also emphasize is that at some point, if your physics-based approach is too good, then what you may see in your residual is just noise. And there's nothing to pick up there, right? So I want to kind of use that as a disclaimer that yes, combining the two is going to have advantages, but they're complementary to each other. So if physics-based model provides very good prediction, then there's not much left for the data-driven model to do, at least in this context.
Okay, let me ask a question online from Kaveh Dagani again. He says, great presentation. How do you incorporate and generalized operational input parameters that naturally could be so different for different cases in your training process?
That's a very good question. So basically, and this is an ongoing work that we're doing. In fact, Jodel is working on that right now. So it's absolutely true. So what we do is we take data from 1,000 wells. We do have well-specific information in that data, which is something we're sacrificing right now in this approach that I showed, because we are basically combining everything as if they are repeated trial of the same thing, which may not be true, right? Now, when it comes to well-specific information, that what we're trying to do right now is, instead of generating global models, we're trying to localize the models. And that can be done either through kind of regionalization of the field, if there is evidence suggesting that different wells in different regions will have a different behavior, or it can be done through clustering mechanism. That's another area that we are investigating now. Can you use the data to first perform some clustering so that you get multiple models depending on which cluster you're dealing with? And that could potentially address some of those issues.
Okay, quite a few questions online, but let's go back to our audience here. Please.
Thank you. I had two questions. So my first question is, if you addressed autocorrelation in your data, I noticed because it's over time series data, and I don't know if there's spatial dependence between wells. So was that taken into account in your modeling and cross-validation, and how does that look like? Does it impact predictive power of model? And the second question, kind of related, is how does data validation look like? Have you taken wells that were maybe nearby and seen how it predicts on just field data?
Yeah, very good question. Yeah, maybe it wasn't clear. So the results that, I start with the second question. The results that I was showing, those were the results from the test wells. So they were not part of the training. So in fact, we do 85%, 50%, depending on scenarios, but we do 85%, 15% scenario for cross-validation, or 20%, 80%. So 80% of the data is used for training, 20% for testing. The results I'm showing are for testing. The first question related to the spatial information between wells. No, we haven't, in this approach, we haven't taken that into consideration. What I'm showing here is trying to really reduce the data, the time series, the correlation that you see in the time series, and take that into low dimensional space to deal with it. However, what you're mentioning is also relevant to our ongoing work, where I mentioned about generating multiple models, depending on if the nearby wells are showing similar response behavior, then that gives us reason to kind of increase the resolution of our model and create regional model as opposed to global model. That would be one approach. But we have looked at well interactions as one of the components that might be missing in our physics-based model, and just to see how this method will perform. But other than that, we haven't done much to consider well interactions or nearby wells, how they communicate.
I guess one follow-up question on the time, because you mentioned you had multiple models. So what do you think is predictive power over what time period?
So what I was showing in here was basically the assumption, the underlying assumption is that you have data for a given interval, let's say sometimes 1 year, sometimes 5 years, depending on the case. And we are looking at learning what the trend in that period is, and then whether we can predict the same trend for other wells within the same period. What makes it much more challenging is that when you have 1 year of data and then you want to actually predict beyond that. That's where you get into extrapolation. And that's what we try to do with recurrent neural network, combining physics with recurrent neural network for time series prediction.
Thank you.
Okay, we'll probably ask one more question online, although there's a few more that you can address later on, Dr. Jafarpour. This one from Russell Johns from Penn State University. Nice talk and approach. I agree with simulation. The simulation is better at predicting differences, residuals, than absolutes. Still, your simulation is dependent on the transport physics assumed and the geometry of the fractures. From intersecting boreholes, there is some evidence that fractures in tight shale reservoirs are in planar clusters. Are you using these types of fractures, and what transport mechanisms are assumed, like advection, diffusion, etc.? How much would variations in these assumptions impact the recovery estimates?
So yeah, there are a few questions there. So I think the short answer is that the results I was showing was basically a simple kind of vertical fracture networks that are connected to our hydraulic fractures. And we wanted to see whether we can basically get the response, the contribution of those natural fractures for production using this approach. Now, in terms of layers and horizontal fractures within layers, we haven't really gone into those kind of details for this approach. But what I would want to emphasize here is that what this method is actually doing is compensating for the missing parts in the physics, which is something we usually don't know what it is in real application. The examples in here just to demonstrate, a simple cases, whether it does what is expected to do or not. But in reality, any kind of, let's say, parameter uncertainty that we have, model description, not just fractures or geomechanics, it's actually trying to capture the lump effect of all of these deficiencies that our models might have. And by the way, also as a disclaimer, there's no way to know what is causing it. It's just a way to follow the trend that you see in the data from a baseline prediction. It doesn't give us any feedback what is wrong in the model. It just allows us to compensate for what is not able to capture and what the data is suggesting.
Okay, well, once again, thank you very much, Dr. Jafarpour.
Sure, thank you.
Very informative, interesting.